Okay, in our previous segment, we talked about damped harmonic motion, and we said that the amplitude gets smaller and smaller as time goes on. So in this graph here, we have the amplitude going up and down, time is going sideways, and if something is being damped, the amplitude is getting smaller and smaller and smaller until finally it goes to zero. Now look at this graph that's right next to it. So this graph over here, it looks similar in that time is going sideways and the amplitude is going up and down. But notice that this time that the amplitude starts out at zero, but then it starts to increase like that. So this is so forced harmonic motion is going to be the opposite of damping. It's going to cause the amplitude to get larger and larger. Now in this case over here, how did we explain it? We said that the system was losing energy to its environment. And so as it loses energy and is escaping into the room, then the amplitude is getting smaller and smaller. So if we want the amplitude to get larger and larger, what must be happening? Energy must be going into the system. In damping, energy is coming out of the system. In forced harmonic motion, energy is going into the system. All right, now, one way that you can demonstrate this is again with the spring. So you're going to take a spring, hang a mass from it, so it's dangling like this. And so if you pull it down and you let it go, it's going to want to go up and down at a certain frequency. Now what I want you to do is don't pull the spring down, so leave it like it is, but I want you to take your hand and to start to do this with it. And what you're going to find is that this mass is going to jiggle up and down because your hand is moving up and down. But it doesn't go into resonance, meaning it doesn't start to do this, until the rate at which you're moving your hand up and down matches the natural frequency of the oscillator. So when you take it and you pull it down and you let it go, it has a certain frequency at which it wants to vibrate at. If you move your hand at that frequency, you'll notice that that mass will, at first, it doesn't do anything, but then it starts going up and down and it gets bigger and bigger and bigger till finally it's bumping into your hand when you do that. So it's going into resonance. So resonance only occurs at one frequency. So when the forcing frequency, the rate at which you're moving your hand up and down, matches the natural frequency of that substance, it then goes into resonance. Every substance has its own natural frequency. So did you notice that if you had a short length on your pendulum, it had a high frequency? If you had a different system, meaning a longer length, it went back and forth at a smaller frequency. Buildings do the same thing. Buildings are different heights. So you can think of a building as being an inverted pendulum. A pendulum does this. A building does this. So during an earthquake, a building can go back and forth and it will vibrate at its natural frequency. But if the frequency of the earthquake matches the frequency of the building, then that building, the amplitude will get larger and larger and larger until it collapses. So you might notice that after an earthquake has occurred, some buildings are unaffected by the earthquake. Other buildings fell down. And a lot of that has to do with the height of the building and then its natural frequency that it wanted to oscillate at, and if it matched the frequency of the earthquake. All right, I got a couple of videos that I want you to watch. So the first one is how to shatter a glass using your voice. All right, so watch that one on YouTube. Go ahead. Okay, pretty cool. All right, so you got this old rocker who has the ability to match the frequency of the glass. So if you take a glass and you ping it, it's going to have a certain frequency. Now another way to do it is to lick your finger and then go around the edge of it, and it's going to produce a certain frequency. If your voice can match that frequency, you can break the glass. Notice he was wearing eye protection when you do that, so you don't want to get glass in your eye. Pretty hard to do, but it can be done. You just need to match the frequency of the glass. Okay, another example. Soldiers, when they go across a bridge, should not march in unison. Okay, because if they're marching in unison, they're marching at a certain frequency. And if that frequency matches the natural frequency of the bridge, it's going to collapse. So that's the reason why they tell soldiers to walk at different speeds and frequencies as they walk across a bridge. The picture there is the Tacoma Bridge in Washington. So watch that video. Pretty spectacular. So imagine that bridge was made of concrete and steel. But because as the wind would blow across the bridge would act like an airplane wing. We'll learn about that in a later lesson. But as wind blows across the bridge, it lifted the bridge. And then when the wind would stop blowing, the bridge would come back down. Now the kids thought that this was great stuff. So they would wait for a windy day, and then if they timed it just right, their car would be on top of the bridge when it was at its top, and then the bridge would drop out from underneath them, and then their car could go airborne. Well, one day the wind was blowing at just the right speed across the bridge that it started the bridge to go into resonance, and the amplitude got bigger and bigger and bigger until finally it broke the bridge apart. Okay, this also, another example of this happened in Kansas City, Missouri, in the United States. And so what happened was that in a motel, this is the lobby of the motel down here, they had these catwalks that went from one side of the building to the other side of the building across the lobby. And so it was New Year's Eve, and you had people that were dancing on top of these things. And it just so happened that they were dancing in rhythm at the same frequency as the natural frequency of these catwalks, and one of them collapsed. And it was really bad because when it collapsed on top of the one that was underneath it, which caused it to collapse, and I think something like 30 people were killed as a result of this. So this is practical physics right here. So you don't want to mess around with resonance and forced harmonic motion. So there are formulas for actually how to calculate the frequency and how to predict how the energy is going to change as a function of time. So there are formulas for that, and there are also formulas for damped harmonic motion. We're not going to do it, so I just want you to be able to describe to me what it is. All right, so we're finished with this lesson, and so let's take a break, and when we come back, we'll take our lesson quiz.